Hello, and welcome to this video lecture on the second part of Chapter 5. I'm going to go through some problems that are similar to the ones I assigned, and hopefully that'll help you get through the assignment. So one of the first ones that I'm going to do is problem number 15. It goes as follows. The percent frequency distribution of a job satisfaction scores for a sample of information systems senior executives and middle managers are listed below, and I've typed those in on the screen. The scores range from a low of very dissatisfied, that's a 1, to a high of 5, which is very satisfied. And so part A says develop a probability distribution for the job satisfaction score for a randomly selected senior executives. So let me go ahead and format this a little better here. I'm just going to wrap this text. And you can see what I've got here. I may have to widen it a little. So we have all this data here, and so what it's asking you is okay, what is the format distribution for senior executives? I could spell this right. So I'll change that. So what we'll need to do is get our total for each of those columns. So I'll just come up here to the sum area. And we see that totals to 100. I'll copy that over. That's 100. So to write the distribution, all we need is to say, okay, what if x is a certain number? What's the f of x of that? And again, so that's our satisfaction score. So for senior executives here, we would just take this total and divide it into this score here. So again, so that would be, if we look at that, that would be this value divided by had a voice recording application going. That's why you saw the text on the screen. Let's start again. This value divided by the total, it's going to be the same each time, so I'll hit F4. We'll just copy that down. And if we were to sum that, that should come to 1. And so that is the distribution for our randomly selected senior executives. For part B, they want you to do the same thing again. Develop a probability distribution for the job satisfaction score of a random selected middle manager. So again, I'm going to put a thick bottom border. I'm going to copy that down. This will be the same, except now it'll be the middle manager divided by that total, which will be absolute. And that's our distribution, and the sum should be 1 again. Part C asks for what's the probability that a randomly selected senior executive will report a job satisfaction score of 4 or 5. So if we come up here and we look, this is for senior executives. We could label that more if you wanted to. But a 4 or 5 probability is 0.42, a 5 is 0.41. So the probability then is this value plus this value. Hold on one second. Just start over, equals this value plus this value. So it's an 83% chance. Okay, so you could write that as probability of 4 or 5. Part D asks for what is the probability that a randomly selected middle manager is very satisfied. So middle manager, very satisfied, would have an X score of 5. So that probability is 0.28. The last step, compare the overall job satisfaction of senior executives and middle managers. What you could say here is senior executives appear to be more satisfied than middle managers. You notice they have higher satisfaction scores at the end, lower satisfaction scores here, whereas middle managers don't seem to be as satisfied. So 41% reporting a 5, and only 28% of middle managers right here in the report are satisfied. The next problem I want to do is problem 17. So it gives you the probability distribution for damage claims paid by the Newton Automobile Insurance Company on collision insurance. And it gives you the payment and the probability. So I've written that distribution here, f of x, matches up with the payment type. And for problem A, it's asking you use the expected collision payment to determine the collision insurance premium that would enable the company to break even. All right, so you take the probability times the payment, and that gives you that value for that particular type of payment. When you sum all that, you should get a 1 here, and you should get a value here. Then this is the expected value. So those are the totals. So the answer is $430. So that's the expected value of the insurance claim. And if the company charges that, then they would break even. So the implications are if they want to make a profit, they're going to need to charge more than $430. In part B, it says the insurance company charges an annual rate of $520 for the collision coverage. What's the expected value of the collision policy for the policyholder? They give you a hint. It is the expected payments from the company minus the cost of the coverage. So the expected gain is $430 minus the cost of insurance coverage, which is $530. I'm 520. And so this is the annual loss expected to the policyholder. So the second part of the question of B is, why does the policyholder purchase a collision policy with this expected value? And the reason is they think they're going to lose money, but if they have a large accident or something, then the insurance company will pick up that larger amount. Okay, the next problem we're going to do is 21, and you're given a university found that 20% of students withdraw without completing the introductory statistics course. Assume that 20 students registered for the course. So A is compute the probability that 2 or fewer will withdraw. So the question is, okay, you're going to do the probability that it's 0 plus the probability that 1 will withdraw or 2 withdraw, right? 2 or fewer. So now the question is okay, what is the distribution of that observation here? So either they withdraw or they don't withdraw. So that's a binomial distribution. So we're going to use the binomial function in order to solve that. So we'll say equals binom. So it returns the individual term binomial distribution probability. So that's the one we want. The numbers is we want 2. The trials, we want 20 because there are 20 students in the course, so each one represents a trial. And the probability here, they told us that 20% of its students withdraw, so it's 0.2. And then we have, hold on one second, we want true because it is cumulative. And that tells us that 20.61% is that probability. Part B says compute the probability that exactly 4 will withdraw. So again, this will be the binomial distribution. Number of trials here, or numbers, will be 4 out of 20. Probability now is 0.2. But now we don't want cumulative because it's just for exactly 4. So we'll say false, and that is 21.82%. Part C says compute the probability that more than 3 will withdraw. Okay, so we can compute the probability of 0, 1, 2, or 3. So the remaining must be more than 3. So that's really 1 minus all of this. Copy that again. And we'll do function of 3. And let's make it a bracket around all of that. So we can compute this part using our binomial distribution. So we can say 1 minus, do this as a function, equals 1 minus binomial distribution, again, 3, 0, 1, 2, 3, number of trials, not trials, it's the numbers. The trials is still 20 because that's how many people have enrolled. Probability is 0.2, and since this is accumulation now, we'll say true, and the answer is 58.86%. And then D is compute the expected number of withdrawals. And so I'm not using the exact symbols, but mu is equal to the number times 20. So our number is there's going to be 20 trials, and we know that 20% of those usually fail. And I can say equals 20 times 0.2. And so that should be about 4. That's the expected number. The next video I'm going to do is number 23. And it says emergency 911 calls to a small municipality in Idaho come in at the rate of 1 every 2 minutes. Assume that the number of 911 calls is a random variable that can be described by the Poisson distribution. What is the expected number of 911 calls in 1 hour? Well, if you're getting 1 every 2 minutes, how many 2-minute intervals are there in 1 hour? 2 go into 60. How many times? So we'll say equals 60 divided by 2. So there are 30 per hour. Okay. The next question, part B, says what's the probability of 3 911 calls in 5 minutes? Okay. So the first thing you need to do is calculate the mean or the expected value of calls for 5 minutes. So we know we get 5 minutes divided by 2, that's how many intervals are in there. So we'll need to have this formatted. Let me do a right click, go to format, and we'll just do general. Still wanting to format it as date. So let me format sales as a number. So that should be 2.5. So equals 5 divided by 2. So that is the expected number of calls in 5 minutes, right? So that's the first thing that we got to calculate. So with that, what we're looking for is what's the probability of 3 911 calls in 5 minutes. So we know this is a Poisson distribution. And so here our X, and we can click on that, is going to be 3. Our expected value or mean is going to be this number. And it's not cumulative, so we just want it exactly for the 5-minute time. So this will be false. And that probability is 21.38%. Now, you could have calculated it out by hand. And if you did so, This is the formula. So that distribution for 3, that density function. So you got the mean raised to the third power, e to the minus 5/2, and then 3 factorial. And that's just the formula that they give you in the book. I find it's a lot easier just to use this function. So let's look at C. C is asking us for what's the probability of no 911 calls during a 5-minute period. So you can set up the formula again. So what we're actually calculating is f of 0, and that equals the Poisson distribution of 0 with a mean of still this value and still false. And the answer is 8.2%. So that's how we get that number. The next problem that I want to do is problem number 26. So it says most computer languages include a function that can be used to generate random numbers. In Excel, the ran function can be used to generate a random number between 0 and 1. If we let x denote a random number generated using ran, then x is a continuous random variable with the following probability density function. Graph the probability density function. So this is a uniform probability distribution. And so we can graph that out by just drawing lines. So we know that for 1, and then we might do 0.5 here. We'll start at 0. And then we know it goes to 1 and 2. So our graph will look like the following. So our y-axis will be that. I need a left border. I'm sorry, a right border. Didn't really show very dark. Maybe I can just draw it. So I moved 1 and 2 down a level, so that represents the x-axis. So I'll need lines above that. So top border. So that does the graph. So the actual drawing then is between, we know that the range is x is between 0 and 1. So it goes there, and what's the probability? It goes up to 1. So what we're actually doing is we're going to draw a box that fills that area. Okay, so that would be the graph for that. So let's go on, and I'll just label this as A, just so you can see. So the B here, this is what's the probability of generating a random number between 0.25 and 0.75. Well, the difference between 0.25 and 0.75 is 0.5. So that's that area of 0.5 here. So you should just subtract the two. So you just put something like the following. So part C says, what's the probability of generating a random number with the value less than or equal to 0.3? So that's just the probability of x being less than or equal to 0.3. And that answer is just 0.3, because if we look at that, it goes from 0 to 1, so that's our area, and so we just do the 0.3 here. Part D says, what's the probability of generating a random number that has a value greater than 0.60? Well, if we look at this, we see it goes to 0.60, and then 0.60, 1 minus that would be 0.4. It has to be greater than the 0.60. Well, 60% took up this, and then greater than that would be the 40%. So you see how that's the 1 minus the 60%. Step E says generate 50 random numbers by entering RAND into 50 cells on an Excel worksheet. Compute the mean and standard deviation for the random numbers in part E. Okay, so we'll say equals RAND. And this is one of those functions that's going to require no arguments, but all functions require parentheses. So we get that. And I'm going to move that over one. And I'm going to do my trial here. And I'm actually going to go up here because I don't want to type 50. I'm going to do a fill, and because this is shrunk down, didn't see what I'm usually looking for. So we'll do this one. We're going to do a series. We're going to do a column. We're going to step value at 1, and we're going to do 50. Hit OK. And if we scroll down, you see it stopped at 50. Now all I have to do is double click this little handle, and it gives me all the random numbers. And we want the mean, so that's going to be the average of all these cells. And the standard deviation for the random number in part E. So type some labels out to the side. So the standard deviation, STD, it's not from a population. So we want this one. It's from a sample. And we can see what the results are. And you'll see that they change every time I change a number, but you would expect on average to be 0.5. And so that just shows you what is being produced here for an average and standard deviation. The last problem I want to do is number 29. So the Siller Construction Company is about to bid on a new industrial construction project. To formulate their bid, the company needs to estimate the time required for the project. It's very similar to what we did in the book. Based on past experience, management expects the project will require at least 24 months. Okay? And could take as long as 48 months if there are complications. The more likely scenario is that the project will require 30 months. Assume that the actual time for the project can be approximated using the triangular probability distribution. what is the probability that the project will take less than 30 months? So the first thing you need to do is just follow the formula that's in the book. So you need to know what the minimum value is. So A equals 24. B is the maximum is 48. And the mode, most often occurring, is 30. So the probability that X is less than or equal to 30 equals, and then you just do the calculation. And the calculation looks like the following. Which you have is the mode minus the minimum squared. Let me rephrase that. The 30 is not the mode. The 30 is your probability of what you're looking for. So that's this 30, not this 30. Minus the minimum value squared. Then we've got the max minus the min. This 30 is the mode. And then you've got your minimum value here. And this is all from the triangular distribution cumulative properties, because it's all less than or equal to 30. And this is on page 198. So the answer is 0.25% using that probability distribution. Part B is, what's the probability that the project will take between 28 months and 32 months? Well, you know your minimum is 24 and your max is 48. So what you're going to have to do is a little subtraction to get the correct probabilities. Let's say this box represents the probability of less than or equal to 32. Well, that also includes less than or equal to 28. So what we've got to do is, when we want it in between two things, let's say this represents the less than 28. So that's 28. This is 32. Well, I can get all of this, but I don't need this part. So now I'm going to take that off. And so that means what I'm left with is X in between 28 and 32. So what we'll need to do is we'll need to do those calculations. And those calculations is just similar to what we did above. And you'll see it's, make sure you can see everything. Spread that out a little. Probably need to move that down. So 1 minus this minus that. Right, that's what we're doing here. So first of all, we have to create the probability of less than or equal to 32. And then we do the 1 minus that because we're calculating everything. And this part is the probability less than 28. So we run all the calculations and the final answer is 29.63%. Part C says, to submit a competitive bid, the company believes that if the project takes more than 36 months, then the company will lose money on the project. Management does not want to bid on a project if it's greater than 25% chance that they will lose money on this project. Should the company bid on the project? So what we need to calculate is the probability that x is greater than 36 using this triangular distribution. So we know all of it represents a block, right? What we want is everything greater than 36. So if we know what the probability of x less than 36 is, that is this block, to me it helps to graph things out. And I can subtract this from everything else, then I'm left with the probability of x greater than 36. So we just run through the calculations again using our formula, and the answer is 33.33%. So that is greater than 25%, so the company should not bid on the project. And so I hope these demonstration problems will help you. Look at those formulas, think about which distribution you need to use, and then you can use the formulas or the functions built into the spreadsheet to do the calculations. And that's it.